That's going to need some work.
Well, engineering challenges. Yeah, I'll try to suss that.
So welcome everybody to tonight's Café Scientifique. My name is Jennifer Cobb. I am chair of the Biochemistry and Microbiology Department in the Faculty of Science at the University of Victoria, and I am also co-organizer of Café Scientifique. And before we get started, I just want to acknowledge where the University of Victoria is located, and acknowledge and respect the Lekwungen people, the Songhees and Esquimalt people, on whose historical or traditional territory the university stands, and also acknowledge the Wasanich people whose historical relationships with the land continue to this day. So the speaker tonight is Kristan Jensen, and Kristan comes to, he's been at the University of Victoria for a couple of years. He was at San Francisco State prior to that. He was born in the Keys in Florida, so far, far away, like across the continent. And tonight he's going to be talking about, and I made a cheat sheet because being from the life science or biochemistry, it's a little over my head at times, and I even have to put on my glasses. So he's a researcher in theoretical high energy physics, and he specializes in quantum gravity, including properties of black holes and space-time wormholes. That sounds really exotic. He also has expertise in string theory and universal entanglement. And my knowledge on that is about like the multiverse Marvel series. Yeah. Anyway, join me in welcoming Dr. Jensen, who is an associate professor in the Department of Physics and Astrology at UVic.
Let's see. I'm not used to talking with a microphone, so can you hear me? They say, okay, use the microphone. This you can hear now. Okay, marvelous. Okay, we're really doing something then. Well, thank you for louder. Okay, that's again. This is very outside of my expertise. Other things are not. Thank you very much for the kind introduction. It's lovely to join you all tonight. I can't really see you owing to the lights shining in my face, but I imagine that as the night goes on after the talk, we'll have some nice chance to discuss. Now, maybe I would like to begin with something a little bit different than in the average talk. I'd like to begin with a question for the audience. Show of hands. How many of you have ever heard of general relativity before? This is not your average group of 100 people. How many of you have ever heard of the fractional quantum Hall effect before? A couple of you, okay. What about quantum gravity? Before the thing that you just heard from Dr. Cobb. Okay. String theory. Okay, lots of you have heard about this. Symmetry-protected topological phases. Landau Fermi liquid theory. Cold atomic gases. Okay. Why am I starting with this? Part of it is to know what I'm dealing with for tonight. But the other thing, so as advertised, I'm a string theorist, and I always find this so funny talking with people, members of the general public, because they know about me, and it's very strange that they do, as you do tonight. I want to share with you a little secret before we get started here, some context about our field, sociological context. So there's about 200 of us worldwide, on the order of hundreds of string theorists that have permanent research positions at universities throughout the world. And to normalize that number properly, one should compare it perhaps with the number of permanent research positions in physics writ large. And this is a difficult number to get to the bottom of, but it looks to be on the order of about 10 to the 5, so 100,000. So we have amazing public relations. So the things that I was mentioning, topological phases, fractional Hall code, these are things that occupy the attention and the tens of thousands of people's time on a nearly daily basis, and you haven't heard of them. You've heard of us. Now, whether that's fair or not, I'm not here to judge. This is the world as it is. We don't get to choose. But just a little bit of context, maybe so you know for yourselves how small of a little corner of physics we really are. Now, why is it that you've heard about us before? Well, probably the reason is that it has to do with the nature of the work that we do. So people like me, our basic task is trying to understand the fundamental laws of nature. Now, that situates us within a somewhat larger group of physicists. So if we're going to perform the Venn diagram exercise, there's a blob of string theorists, including people like me. And then there's a larger blob that surrounds it that could be denoted as particle theorists or theoretical high-energy physicists. Term varies depending on which funding agency is funding the people involved. But, okay, there you have it. Within that vein of physics, the main questions that the people have, the things that guide our research activity is, first off, what are fundamental constituents of the universe? And second, what are their fundamental interactions? And the string theorists in particular, the angle that we have on the problem that's particularly unique to us is that we want to describe the marriage of quantum mechanics and gravity. Now, in describing the aims of our field, you will notice that there's nothing in there about technology or benefit to human society or what have you. Our research, I want to kind of emphasize this point at the beginning, our research is very basic in nature. It's very fundamental in nature. And the sort of questions that drive us are, sometimes people might say, oh, well, maybe someday there'll be some technological benefit from it. You're here tonight, let's be honest with each other. I'm going to disillusion you of it. That's not the reason why people engage in this. That's not the reason why people like me do this. That's not the reason why there's a very small fraction of physicists pursuing these questions. It is, in the parlance of NSERC, which funds a lot of people here in Canada that do these kinds of things, curiosity-driven research. We do it because human beings want to know, and because we live at this beautiful point in human history where we have the technological means and the resources to not send people like me to the fields, but send them to the Elliott building on the UVic campus instead to think about these things. Okay, so what is my goal tonight? I want to give you some very idiosyncratic perspective on questions having to do with string theory and quantum gravity and so on. And part of the perspective I want to give you is something that you might not hear in a documentary. Now, it still boggles my mind that there are documentaries, there are books that perhaps even some of you have read or watched about us, the kind of things that we do. So there are resources out there if you do want that are accessible to the general public that you can learn more about. I want to give you something that you would not get from those books or those documentaries, which is some perspective. Why are people doing this? What is kind of driving the research from the inside? Now, let's see. I have to keep going from my notes from time to time here. Apologies. My day started approximately 19 hours ago in Boston. Okay, so I mentioned earlier that very few scientists study these things. Very few of those still study strings these days as a candidate theory describing all of nature's interactions, all of her laws. That may be a bit of a surprise to you. Perhaps you came in thinking, this is some of the spiel that people do and the general public do here about strings, is that it is a candidate theory of everything. Those are the words that are sometimes used, a theory of all of nature's laws. And that may yet be true, but that's not what people are using it for these days. I want to help you to understand a bit of why that is. Even so, it still continues to be an extremely interesting wellspring of ideas that continues to shape our field. Now, let's see, a little bit more context. We talked about where strings is within particle physics. I should back up even further to talk about sort of, what physics is like more broadly from the inside. So we'll zoom out, and then we'll zoom back in again to the questions of interest to string theorists these days. So physics is an extremely mature discipline, dates back before the time of Christ, thousands of years filled with incredibly smart people making fundamental contributions to it across the ages. Well, that being said, there's a stark line in the sand, if you will, that divides that activity, say in the time of Archimedes and the Greeks and in the Middle East and so on, and the present day, and that for practical purposes, that line can be drawn about 350 years ago with the invention of calculus, and shortly thereafter, the work of Isaac Newton. During that time, well, really that last 350 years, we have gone as a species to being able to develop a very predictive and accurate framework describing phenomena, the laws of nature, both here on Earth, in the heavens above, and everything in between. And the examples sort of highlighting what has physics successfully uncovered are myriad and remarkable, and it's worth pausing for a moment just to kind of revel in the magnificence of it all. In the time span that we're talking about, 350 years, it's not a long period in human history. So let me give you an example. There's something called the perihelion of Mercury. Has anyone here ever heard of that before? Okay, a couple hands, something. So Mercury, you might have heard about that one, that's a planet. It traverses an orbit around the sun. That orbit is not exactly, but it's very, very close to being an ellipse. So it goes around, and to very good approximation, what the orbit does, that elliptical orbit, it kind of rotates a little bit each year. You can quantify how much the orbit rotates. So each one looks like an ellipse, but then the path that it takes, it's like a spirograph, if anyone had those with their kids back in the day. I still played with those, although, and our kids do, but I don't know how common it is anymore. Maybe if they put one on a phone. Anyway, so the way that you quantify the change, the rotation in the orbit, if you take a circle, divide it up into 360 degrees, take one of those degrees, chop it up into 3,600 parts, so how many seconds there are in an hour, each of those parts is called an arc second. The orbit of Mercury changes by 5,600 arc seconds every year that it goes, every Mercury year, not every Earth year, but every Mercury year. So a little bit more than a degree, about 1.5 degrees. Now, to give a sense of the predictive framework and the things that people have been able to come up with, at about the time of Einstein in the early 20th century, physicists had been able to predict what the perihelion of Mercury should be, as well as to measure it. And the prediction is based off of other planetary bodies in the solar system and how heavy they are. And that prediction was for 5,557 arc seconds every Mercury year. And the actual number that was observed was 5,600. And again, this is a fantastically small effect. This is probably not something that you would wake up thinking to yourself, that's not what's going on. So to be able to and physicists realized that there was a problem. This is one of the problems that was successfully addressed when Einstein came around not too much long after that with his general theory of relativity, describing gravitation in our solar system, in our galaxy, in our universe. There are some effects in gravity that were not understood at the time of dawn of the 20th century that are then accounted for in Einstein's theory that describe the remaining 43 arc seconds of precession in Mercury's perihelion every year that take you from 5,557 to 5,600. and you get it on the nose. It works remarkably well. That's an example. That has to do with just things that, in principle, you know, if you have a good enough telescope and good enough graph paper and you're patient, or maybe you have some graduate students working for you, that you can figure out. Here's another. There are elementary particles that you may have heard about, things that can be produced in colliders or in radioactive processes. An example of such a particle is something called a kaon. They come in 4 different types. They all decay. They're unstable. They are unstable to various decay byproducts. 2 of them are electrically neutral. They're called the neutral kaons. And they're called affectionately by particle physicists K short and K long, as one of them decays faster than the other. They oscillate into each other. So if you make one of them in some process in a collider, and then you wait a little bit of time, it'll oscillate into the other kind of kaon, and that can be observed. And the frequency, the sort of how fast they oscillate into each other, can be predicted. And again, this, you know, does it work? Does it match what is observed? Well, if I'm up here, you can infer what the answer is. It works incredibly well. Here's another example from particle physics. Electrons, if you put them in a magnetic field, their energy changes very, very slightly. If you put them in a small amount of magnetic field, and then you look at the ratio, how much does the energy change by, divided by how much magnetic field is applied, that gives you something called the magnetic moment of the electron. And that number, in some units, it's a dimensionful quantity, but in some natural choice of units that particle physicists like, where they set as many things as they can to 1 as they possibly can, including the speed of light, because why not? That number is 2 plus a very, very small remainder. 2 is what's predicted by something called Dirac equation that you learn about in, say, in a second semester, 4th year undergraduate course in quantum mechanics. And the remainder is some incredibly tiny number that has been measured accurately to 10 significant figures. And it's been predicted accurately to 10 significant figures. This is something that comes, I'll spare you the details. Even I don't understand, it's beyond me because it's a lot of technical labor. It comes from something called Standard Model of Particle Physics. It incorporates all of our insights from quantum mechanics, quantum field theory, special relativity, blah, 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 blah. And does it work? It works. It does. It's amazing. It's the most precise agreement between theory and experiment in all of science. This is the kind of field that shapes us, the people that are in it. And as you can see, the standards are high. The questions are much simpler, perhaps, than other things that people consider. But remarkably, we can get a real handle on it in such a way that stands the test of time. In building up all of these insights, it's not the work of one person or even just a few people. It's really a community of people that has shaped this and has along the way developed many traditions that have kind of guided our research, that have guided thinking and the discourse around it, to also to make sure to shape that the things that we advertise as discoveries really stand the test of time. I'm going to mention a number of those traditions, and the reason why I'm going to mention them is to help give you some sense of that those traditions that I'm going to outline. It will make a lot more sense than why there are a small number of people like me doing string theory. So I'm trying to, again, go zooming out, zooming back in. Before doing it, I do want to make one other aside. Maybe this is breaking the flow of the talk a bit, so apologies. But even as a practitioner, when you step back and you look at all these things, you know, you prepare it on a day-to-day basis. Like most of my life is spent trying to hunt down factors of 2. I have a former student who worked with me last summer that was what his research project was for me for much of the last year. or did all sorts of technical things, and then you prepare a talk like this and you take a step back and you gaze in wonder at the whole thing. It's really remarkable what a confluence of events there have been in the last 350 years for us to even be having a discussion like this. We need, in order for all of modern physics to proceed, we need the mathematical language in which to describe it. We need the experimental capacity to do things like, well, have extremely precise telescopes that can measure the 43 discrepant arc seconds of perihelion of Mercury. We need, I mentioned earlier, let alone, the anomalous magnetic moment of the electron to 10 significant figures. We need particle accelerators. We need the technological know-how. We need the right ideas so that we aren't just wandering around lost, scratching our heads. We need the right technology. We need the right cultural norms to promote this kind of basic research. We even need there to be enough kind of extra resources in society that some of it can be siphoned off to things like this and still make sure that there's bread on everyone's table. And this is a remarkable thing that all of those happened at the same period in time and that it aligned so well. Not guaranteed that it would happen again. Okay, so that's my aside. I'll come back to that a little bit later. What are some of these traditions that I'm referring to that kind of shape our field? And the first one, I made a list. I like lists. I even numbered this one as just a 0 because we sort of take it for granted sometimes. It appears that the right language to describe laws of nature is mathematical in nature. And mathematics that human beings can understand, which is very surprising. Like, it did not, you can imagine, why is it that way? No one knows, of course. It simply seems to be that way. Another tradition in our field that has changed a lot over the last 100 years is that, well, we're very practical, much more so perhaps than if you were to crack open papers of physicists 250 years ago. So what do I mean by practical? I mean the governing question that guides a lot of our research is not, well, what's the reason why you made some theory or why you were studying this thing? The questions really are, does it work? Are you able to make predictions? Do they actually match experiment? Are you able to measure the thing? It's dreadfully practical in nature. What, sorry? Oh, that was someone talking with the waiter maybe. Okay. Another major tradition, another major lesson is that nature is probabilistic. In particular, she appears to adhere to all the postulates of quantum mechanics to as high of accuracy as has been tested, very systematically, very robustly, very skeptically for over a century. Here's another one. Physics appears to, this is one is a bit more technical. I have to explain myself. Physics is organized according to energy scales. What do I mean by that? Well, let me put it this way. So if we want to predict what will happen if I drop the microphone, how long will it take for it to hit the ground maybe? We don't need to know what is the lightest, or the energy of the lightest possible black hole that can be made when we collide two protons together. We don't need to know that. That's an example of what I'm talking about. The thing that I just said with colliding protons together to make a black hole is something that no one has ever done. In principle, it can be done if you do it strong enough, hard enough, if you have the godlike powers to do so. And that is an actual physical question that you can ask. What is the lightest possible black hole that could be made that way? Doesn't matter a lick if we're talking about making predictions for observable phenomena here on Earth. That idea has been turned into something very actionable. There's a guy whose name perhaps you've heard of, maybe not, named Ken Wilson in the 1970s, who's probably most responsible for making this insight and for putting it to work. In particular, there's a cousin of that idea, which is that we can very sharply, using modern frameworks in physics, quantify our ignorance of very high energy physics when making predictions for things here on Earth, whether it be the dropping of the microphone experiment or studying the motion of many electrons in a metal or what have you. The last tradition that I had listed on here is that of Gedanken experiments. Maybe some of you have heard this word before. Gedanken is thought in German, as I understand it as a non-German speaker. When we take physics classes, we get very limited smatterings of physics history along the way. Mostly you're just trying to learn the actual physics. And here and there you get little snippets of what is passed on to you supposedly as history, including this one, that there's this, that Gedanken is thought in German. So if it's not, please someone correct me after, but not now. So the idea here is something that really goes back to Einstein. It's something that is one of his legacies in our field. The idea is to say, well, look, when we write down theories of what's happening in nature, possible laws of nature, we should take them super duper seriously. Not his words, these are mine. Take them super, super seriously. Push them to the uttermost. Imagine the most extreme circumstances possible, unreachable, unattainable by humans, but imagine it anyway, and ask if something breaks in your theory. So for instance, Einstein asked questions about, what happens if I have two trains passing each other at 9/10 the speed of light? We're not doing that anytime soon. But you still ask the question, and you see, does your theory hold up in these extreme circumstances, in the absence of being able to do an experiment that would settle the matter definitively one way or the other. Now, all these traditions, I'm mentioning all of them because they shape our work in theoretical particle physics and in strings. Let's see, I also have a note here. I've been patting myself on the back for, oh yeah, here we go. So for various successes that we're able to have in physics, the perihelion of Mercury, the kaon mixing I talked about, the anomalous magnetic moment of the electron. We don't understand everything. I should make sure, many of you were raising hands earlier indicating some knowledge of strings and quantum gravity. You probably know then that there's things, very big things that we do not understand. One of the ones that shapes our field, those of us that are thinking about strings, is certain Gedanken experiments that can be performed using gravitons. What are gravitons? Well, in nature, gravity is very well described by Einstein's theory of relativity, in which we can have a whole talk just about this, in which the shape of space-time itself is something that fluctuates, that's a dynamical thing that responds to the presence of energy and momentum in the universe. So our sun at the center of our solar system carries a lot of mass, carries some angular momentum, and it deforms the shape of space-time around it that we perceive on Earth as gravity pulling our planet towards the sun, keeping it in motion. That same theory, if you start treating it quantum mechanically, asking how does gravity behave quantum mechanically, you discover the existence of a particle that has yet to be discovered by people called a graviton that you could think of as the smallest excitation of a gravitational wave. In the same way that a photon is the smallest possible constituent of light. And we see gravitational waves. They're emitted, for instance, the simplest way to know that they exist, that they're out there, is that there's astronomical systems of binary stars that orbit each other very close, and they slowly get closer and closer together. They're losing energy. And the rate at what are they losing energy to? Well, it's predicted to be, and it matches the observations extremely well, to fluctuations in the shape of space-time, gravitational waves. Graviton is hypothetical smallest possible quantum mechanical excitation thereof. Now, with that out of the way, Gedanken experiment. This is how it goes. Take two of these gravitons and scatter them together off of each other, collide them into each other at exceedingly high energies. Well, if the energies in question are of order 10 to the 19 times the mass of a proton in C equals 1 units, E is mc squared, so if C is 1, then energy and mass have the same units. So 10 to the 19 times the rest energy of a proton. And, well, everything that we know about quantum mechanics and so on and gravity will break down at that scale. The technical statement is that the probability of the two gravitons scattering off of each other, nature is probabilistic, the probability exceeds 1, or meaning it exceeds 100%. And if you know anything about probabilities, then it's not quite right. Something's gone wrong. Something's gone amiss. Now, 10 to the 19 times the rest energy of a proton is about 10 to the 15 times higher than any energy scale that has ever been accessed by humans, including at the Large Hadron Collider at CERN in Switzerland. It is, for all practical purposes, out of reach from the human race by direct means, possibly ever. So this is a true Gedanken experiment that we're talking about, this problem that I just mentioned. But it still tells us that something is missing. And it tells us that something is missing from our understanding of physics in a way that's fundamentally different than other things that you might have heard about. Let's have another show of hands thing. How many of you have heard of dark matter before? Oh my gosh, this is making my... Okay. What an audience. Okay. You guys are great. Okay. So you've heard of dark matter. You know then that... Not the beer. Okay. Still getting used to that here on the island. Okay, we'll redo this again. So, excising the beer, we're talking about dark matter in nature. How many of you know of this? Have heard of this before? Okay, there's still a lot of you. Okay. Roughly speaking, when astronomers look out into the sky, they see that there's about 7 times more gravitating matter than is accounted for with visible things like stars and galaxies and such. And the missing mass, whose existence is inferred because it pulls gravitationally on galaxies and stars, is affectionately called dark matter, and there have been many efforts to find it. None have been successful so far. Probably it's at very low energies, very low masses. We have people here at UVic who specialize in coming up with models for it and new ways to try to test and locate it in nature. That's something that's a gaping hole in our understanding of basic physics, 7 times more important than visible matter in the universe. But there's extremely good reason to think that the sort of accounting for it, that it can be done using our existing knowledge of fundamental physics, that it requires something new, but in a way that's almost like putting Legos together. I need another kind of Lego that I build in. It can be accommodated. This thing that I was mentioning with graviton scattering is on a fundamentally different footing. Well, maybe I should mention this to go back to this comment about physics being organized by energy scale. There have been situations historically in 20th century physics where there were similar discoveries, similar problems. Fermi, the same Fermi who was partially responsible for the uranium pile reactor at University of Chicago as part of the Manhattan Project, this Fermi had an effective description of nucleon scattering. Take 2 protons, scatter them off of each other, how does that go? And in that description, probability of nucleon scattering, once you collide them together with enough energy, probability exceeds 1. That can't happen. Something has to come in and fix up our theoretical description of that process. And indeed, nature obliges very nicely. There's new physics that appears exactly at the energy scale in question. The particles that do that ensure that probabilities do not exceed 1, are the electroweak gauge bosons, so-called W and Z, or W and Z rather. Now, with that in mind, there's some reason then to think that there's some new physics that comes in at these very, very high energies. And the working assumption that most people like me have is that they're black holes. They're very, very light black holes, the lightest possible. And, well, this kind of gets us to into the thing that I'm supposed to talk about tonight, which is the study of quantum gravity. How does gravity and quantum mechanics, how do they marry together? In order to have a description that does the job, it's going to have to be something that is that's strong enough to be able to describe the quantum mechanics of black holes and how they can be created and made in sufficiently violent extreme processes, which we are not seeing here on Earth. Now, this field is not a new one. It's about 50 years old now or so. In some sense, its historical antecedents go back maybe another 20 years before that. And because it's a 50-year-old field with some extremely smart people working in it, it is a reasonably mature one, and it has a number of results that are, well, they're quite interesting. And I'd like to share a few with you tonight, as well as some of the questions that those people are studying. And it should be understood in all this that everything that I'm saying from here on out, this is purely theoretical, but it is following within all the traditions that I mentioned earlier. It really follows from taking all of those 20th century principles of physics super duper seriously and following them as far as we possibly can and see if they break. So one lesson that we get from people that study quantum mechanics and gravity together that seems to be quite general, might even be true of the world that we live in, is that gravity is emergent. What do I mean by emergent? Well, let's see. So there are several theories by now, and by mathematical models that people write down of gravity and quantum mechanics that appear to be consistent, that have survived every Gedanken test that has been thrown at it by very smart people. And in all of these things, gravity is not built in from the get-go. It emerges out of other constituents, out of other building blocks. This is the case in string theory. The kind of building blocks in string theory are quantum strings moving around in a higher dimensional space. And out of that, gravity is some emergent thing. You don't put it in there by hand. It comes out as some emergent interaction between strings with each other. There are models of very large random matrices. Really, really big. Think square matrices. And out of those, there are funny theories of both space-time and gravity that emerge. There are other descriptions. This is extremely recent. I was in Boston because I was visiting some colleagues at Harvard that have just been working on this stuff in the last year, where they look at some models that have very large matrices and so-called large random tensors as well. And, okay, it doesn't matter what these things are. The point that I'm trying to make in all this is that these are the only known models of gravity and quantum mechanics together that people can make sense of at a theoretical level, that survive all the tests that have been thrown at it. In all of them, gravity is not built in from the get-go. And there's some reason to think that that's deep, that will be true of our world as well. That gravity, and remember what we were saying about Einstein earlier, gravity is really the shape of space-time. That gravity and therefore also space-time are some emergent properties of more fundamental building blocks that we have yet to uncover. Now, I should mention too that these three examples I was mentioning, strings and large random matrices and tensors, all of these examples are actually various versions of what could be called string theory. And so we're getting into not just lessons that have been provided by this line of research, but I want to give you a sense of why people study it. Part of the reason why is because the only known consistent models, and people have tried very hard for decades, that marry quantum mechanics and gravity together, they appear to the only ones people have been smart enough to find so far have been string theories. Remember when I said earlier that our field is dreadfully practical? The only models that you have, if you're interested in these questions, and the only models that you get to study then that work, that haven't died yet, are string theories, well, guess what you're going to be studying, or guess what you're going to be working with. Now, for this audience, where I guess I can presume perhaps a little bit of prior knowledge, maybe you've seen a documentary, or maybe you've read a book at some point about hearing about how string theory is very mathematically beautiful, this, that, or the other, or various reasons why people were thinking of it as a candidate description of nature. That was perhaps the case 40, 50 years ago, and that was enough to get them going. The reasons now are a bit different. Sometimes the phrase that people use is that it's the only game in town. So if this is the sort of thing that you're interested in, and you want to study it, if you want to work on it, if you want to make progress in it, well, there's not really any other viable candidates that human beings have been able to come up with so far. And I should qualify these statements too and say that there are communities of other very smart people that have been actively working trying to find such alternatives, albeit without success, or when they do find it, it tends to somehow be a really extreme limit of string theory. So, right, circling back to this thing about gravity being emergent, I should stress that all the notions that I was talking about, where gravity emerges from some quantum mechanical strings or from matrices or what have you, this is a very different kind of emergence than what you've seen before. And you might say, seen before, what are you talking about? This is a funny word that you're using. What are you talking about? All of you have encountered some form of emergence before, and I know it because I can see it in the glasses and the bottles on your tables that I'm going to get to partake in after the talk, apparently. So microscopically, the liquid in your bottles and your glasses and your etc. It's made up of molecules. These are all very, very, very tiny. Their collective behavior, when you have enough of them, is not that of individual molecules anymore. What is it? It's a liquid. It's a fluid. Out of all those microscopic building blocks, something emerges that's very simple, that's very macroscopic, that's very observable, and it's just the fluid in your cup. Gravity, and I guess I should say there are more sophisticated examples in physics where there are fundamental forces, versions of electromagnetism, or even of so-called gauge theories, that are not present between microscopic building blocks, but appear as a collective description at low energies once you account for how many degrees of freedom you have, all the stuff that's there. Sorry, I shouldn't be saying words like that. Gravity does not appear to be like that, unlike other fundamental forces. If it's not there microscopically, it's very, very difficult to get it as some emergent property, some collective behavior of all your degrees of freedom at observable scales. In fact, there's a theorem, to the extent that there's theorems in physics, called the Weinberg-Witten theorem to this effect, proven by Steven Weinberg, who is the guy that helped put the Standard Model together, and Edward Witten over at Princeton, quantifying the sense in which gravity is different. Gravity doesn't emerge from non-gravitational degrees of freedom, non-gravitational building blocks, unless you meet certain conditions. In particular, those degrees of those constituents have to be in some other, they have to almost be physically inaccessible. And that is the case in all the examples that I mentioned with strings and random matrices and so on. So that's one lesson that has been provided by, well, 50 years odd research in quantum gravity. Another one is that, well, at the outset, when people were first talking about string theory, it was hoped that, okay, and I am not talking about the route by which people got to string theory or any of the history involved, because again, you could watch a documentary on that. My time is limited. I want to give you some perspective that you wouldn't get from a documentary. So apologies, but I know that's a little haphazard, but I'm standing, I guess I'm standing by my choice. In the early days, people had hoped when they wrote down string theory that there was a unique version of it, that there was a single unique string theory that would be a good candidate description of nature, a complete description of nature, and that ended up not being the case. And the reason why they thought that is kind of interesting on its own right, but what they was soon realized afterward is that string theory is a framework. Much like quantum mechanics is a framework, or if you've heard of quantum field theory is a framework. If you even have taken an introductory physics class where you learn about Newton's laws of motion, you can think of saying, well, asking the question, well, how do I write down laws describing some forces for some particles interacting with each other? You can imagine many possible things that you could write down for such laws. And string theory strongly constrains what those laws might be, but it doesn't give you a unique choice. It gives you many possible choices. In particular, in the 90s, it was realized that if you ask the question, how many possible versions of string theory appear to be consistent with our world, there's about 10 to the 500 of them, which is a finite number. But it's impossible to resolve, which of those is the fundamental description of our world, unless you have godlike powers like those alluded to previously, where you're able to collide particles at enormous inaccessible energies and see what happens. For this reason, the practical attitude of our field has shifted from one where you would say, oh, well, let's have the theory of all things, to, well, we have a theoretical laboratory where we can reliably and consistently study the marriage of quantum mechanics and gravity. It's the only one that we know of, and this is what we have decided to do with our lives. So let's use it and see and push it as far as we can and learn as much as we can with it in the land of thought experiments. In particular, using all of the insights from 20th century physics and taking it super seriously. Now, in the last little bit of the talk here, I want to, actually, maybe I should check the time. Okay, yeah, I'm going to wrap up really fast here. In much of the research, because it's gone a little slower than I had thought, much of our research activity in the last really 25 years or so, as far as like theoretical laboratory and thought experiments and so on that have been performed, has been in the context of black hole physics. And part of the reason why is that, well, in many ways, they're the most extreme systems, physical systems that we know of. One of the most interesting things that you learn about them, let me back up a second. Most of the questions that string theorists ask when it comes to black holes, what kind of thought experiments would you do with them? In a quantum theory, you don't get a choice about what is quantum and what is not. Everything is quantum. And so in a theory that describes quantum mechanics and gravity together, in order for it to be reasonable, it has the black holes that we see out in nature, like the one at the center of our galaxy, have to be consistent with the laws of quantum mechanics. Does that actually work? It's a very hard question to ask. It's one that's inaccessible for experiment, but it's one that at least theorists can pose and try to make progress on. So to give an example of such a thing, in general relativity, it was realized in the 70s by Hawking and Bardeen and Carter and Werner Israel, who was also here at UVic until he passed away quite recently. They wrote a series of foundational works that are now known as black hole thermodynamics, showing that black holes, at the time, people had not found them in nature, this was purely hypothetical, that they behave like thermodynamic objects in the sense that they have an effective temperature, that they have an effective what's called equation of state, if you've taken courses in that. In particular, they have a notion of entropy that is huge. Entropy, when we talk about something like the gas in this room, is really a statistical physics notion. It's a measure of indeterminacy. There's on the order of 10 to the 25 or so molecules in this room, excluding us, of air moving around in this room. And as you can imagine, they can be arranged in all manner of different possible ways. And entropy is a quantitative way of describing how many different ways could they be arranged, and we still have the same experience of air at the observed temperature and pressure that we feel when we're in the room. Entropy is the logarithm of the number of such ways. And there's a result that these guys found for the entropy of black holes. It's roughly the area of a black hole event horizon in units of Newton's constant. And a question that you could ask, is that entropy some measure of how many different ways the black hole can be arranged in such a way that you get the same macroscopic physics? That is kind of secretly a test of asking, do the black holes, are they consistent with quantum mechanics? Another question that you could ask, I'm going to list a bunch of questions and then I'm going to tell you a few things that we know about it. Another question that you might ask is the following. So there is a much larger group than string theorists that study the properties of materials with many, many constituents. Think like order 10 to the 23 electrons in a metal or in some material and how they interact with each other. And one of the lessons that those people have found, these systems with many, many constituents, many, many possible ways of arranging them, is that, well, they behave what's called chaotically. And there are the right thing to kind of characterize those systems by is not the precise arrangement of where all the electrons in the metal are, but rather certain statistical properties. One of those statistical properties has to do with exactly what kind of energies the system can assume. Usually what happens in quantum mechanics is that if you have a system, a physical system, like electrons in a metal or what have you, it can only have certain allowed energies. They're quantized. They can't be continuously arranged. You can have this energy or this energy or this energy. And the differences between those energies are called energy splittings. And the statistical distribution of those energy splittings in systems with many degrees of freedom obeys certain universal scaling laws that have been uncovered in this community. And it's a very general property for quantum mechanical systems with many, many constituents. And you could ask, do black holes respect that? What would we even compute or what would we even measure about black holes to answer that question? Another thing that you could ask, we said earlier that probabilities better not exceed 100%. Black holes in nature, this has not been observed. This is a prediction of general relativity and everything that we know about quantum mechanics, that if left on their own, if they're isolated, they evaporate. If you wait enough time, a black hole will emit radiation. How this is consistent with everything falling in, we can talk about. They'll emit radiation and eventually die off. And if you wait until the black hole is pretty old, until it's emitted half of its mass away, then, well, it's supposed to be, it turns out it's supposed to have a high degree of correlation between itself and all the outgoing stuff in such a way that if you don't do things properly, it looks like probabilities exceed 1. What's going on? Okay, in the interest of time, let me say that so I said that questions like these have occupied a lot of our time over the last few decades. We've made enormous progress on all of these things, but there's still lots of work to do. in particular, in all cases that where we have really good theoretical control over black holes in string theory, it does seem that they, obey the laws of quantum mechanics, that, for instance, they have different ways that they can be rearranged in such a way to reproduce what I was saying earlier, their entropy. That when they evaporate, that this is done in such a way as to respect the laws of probability. And furthermore, and this is part of my own contribution to the matter, that there are scaling laws describing the different energy levels that they can have and the different differences between their energy levels. And I could comment on a lot more, but we don't have time, and I guess maybe I've misused even the time that I've been given. So let me say that I'll end by saying, that we could give a 10-hour version of this talk. There's so many things that I'm skipping over, that I'm alluding to, that I'm almost assuming prior knowledge of, which is probably a bad idea. But there's a wealth of things here, and I'm really looking forward to our back and forth in the Q&A. And thank you very much for your attention.
Thank you very much. You blew my mind. Questions for Kristan? Yep, question here.
Do you think that the largest challenge currently faced by the field is a new approach, or is it a practical, technical? We just don't have the tools to test the theories that we already have.
So I'm going to repeat the question because it's being recorded and because of the live stream and because people in the room could hear you, but not those guys. So the question that was just asked is, in my opinion, what is the biggest challenge that is set before our field? Is it the practical one of experimental reach? Is it that we need new ideas? Biggest is doing some work there. I would say the biggest is a practical one. The way that I outlined that I gave the talk, I think maybe it all comes back now. So the approach that people like me really have ultimately is a very conservative one in nature. We're taking all the insights from 20th century physics and we're pushing them as far as we possibly can. Is that the right thing to do? Well, normally, you would let experiment tell you if you're screwing up or not. Here, that seems out of reach. So ideally, what I would like is for nature to tell us if we have the right ideas or if there's something missing or not. So from that point of view, I would say that is probably, at least in my opinion, the biggest hurdle that we face as a field. Otherwise, where are these ideas coming from? Well, they're coming from other regimes, and we're extrapolating to very extreme ones. But admittedly, too, that goes hand in hand with needing better ideas. All the progress that I was outlining has come from being informed by nature and being able, like this confluence of events that we were talking about, where experimental reach and mathematical sophistication and money to do these things all came together at the right time.
Question?
The string theorist, how many dimensions do you work in and how are they arranged?
Okay, so the question is, as a string theorist, how many dimensions do I work in and how are they arranged? And the answer is, it depends. So there are, so what you're alluding to, I believe, is that when physicists like me write down string theory and you ask what prediction does it make for the dimension of space-time? The prediction that it makes is either 10 or 11, which is not what we see. There are, now when this is, the statement about the either 10 or 11, it's kind of, what's the way of putting it? when you teach physics, you realize what do you do when you teach physics? You teach things at some very basic level the first time, kind of as things were understood in the 19th century. And then you give a better, more honest accounting where you undo some of the lies that you told the first time around. And then you go back and you progressively become more honest in your instruction. And this 10 or 11 is an example of one of these pieces of storytelling that is not, like, it's getting at something that is true, but it's not quite what's going on. There are, for instance, this limit that I was talking about earlier of where random matrices are generating gravity. That the example there, how many dimensions is that? That can be thought of as either no space and just time, or even maybe one space dimension and one time. So not 10 or 11, but some other example. And there's other kind of mathematical ways of building string theories where the place where gravity happens is even exactly four-dimensional. It's just that there are difficulties when it comes to like practical difficulties for a string theorist of how to make it look like the world that we live in if you want to do that. In particular, where there is a very small degree of acceleration in the universe.
Here?
All of this sophisticated mathematics is happening inside your mind. And I wonder whether it's just a look at your mind. It's like out there we describe what we think we're seeing out there, but we can only do it in terms of this inside here. So is there a boundary? Is it recognizable, or it doesn't matter?
Right. So the question is maybe, can I try to rephrase and then shake your head yes or no if I'm getting it either right or wrong? Is the mathematics that we're talking about to describe all these things, this mathematics is written down by humans. It's plopped down on paper by humans. It's thought about by humans. How do we know if it's really the right thing describing nature or not? Is that a fair representation of the, okay. And the answer that I would get to so of the various traditions that our field has generated, particularly over the last century, the real standard is not, is it nice math? Does it make sense? But it's, does it work? Take the property, like, for instance, the perihelion of Mercury, or any of the things that we were talking, or any more besides. Did you get it right? And one of the jobs of physicists is to keep pushing. You get it right, okay, great. Now let's measure it to increasing precision. Let's predict it to even better precision. Because when you make predictions, they're never exact ones. They're approximate ones with some error bars. And you keep going and you keep going until you see if there's a problem. So the answer that I would give is that, and it goes back to this question of, is mathematics as we understand it really the natural language for laws of the universe? It's a working hypothesis, and we push it, and the real proof is in the pudding, as it were. You keep pushing and you see it, does it work or not.
Question back there, and then here.
It's a muddled question after having some dark matter.
Looking forward to that.
Gravitons, you mentioned them earlier on, and then black holes and evaporating black holes emitting radiation, something we can measure. Gravitons, something as yet unmeasured, seem to be very implicated in black holes as being a kind of vortex of perhaps gravitons. So dark matter theory would be that somehow the gravitons have now transmuted into something you can observe.
Let's see. So let me try. So the question that you were working toward, you were talking about three things. You were talking about gravitons, hypothetical particles, black holes, regions of space-time where gravity is so strong that nothing escapes, and dark matter. I'm wondering if there are connections.
Just the beer.
Oh, okay. I couldn't tell if there was an actual physics reference in there. Okay.
Black holes are evaporating
Yes.
by
Yes.
radiation, something that you can measure.
Yes. Black holes evaporate. That's something that can, in principle, be measured.
Nothing. But there was, presumably, lots of gravitons in that field. And where have they gone, or have they somehow evaporated too? Into
Right.
radiation?
Well, so so if the question is, okay, so we did go over this quickly. That black holes evaporate. And then what happens to the radiation that they emit when they do so? We're well past the looking glass now. That should be very clear, right? In the sense that gravitons are theoretical particles. The radiation that I'm talking about has so far been unobserved. So this is, taking our theoretical descriptions of black holes and trusting them in regimes that have not yet been measured or confirmed experimentally. With all of that blah, blah, blah out of the way, the answer is just the radiation's emitted and it flies off. And that's it. So in the same way that if you have a light source and you were to turn it on for a moment, it emits light, the light propagates outward in all directions, and it flies off at the speed of light. From the light source, you turn off the light keeps going. That's a pulse that's going outward.
You're the theorist.
Yes.
Your theories say that those gravitons change into another energy that is that radiation.
Well, sorry, when I say radiation, good. Maybe this is the point of confusion then. For me, radiation is it's sort of a free-for-all term. I don't just mean light. So it sounds like what my comment was being interpreted as saying is that a black hole can emit gravitons, which then get converted into radiation in the form of light, for instance. And for me, radiation is more of a catch-all phrase. Sorry, it's very difficult to give a talk where you don't accidentally launch into little snippets of technical jargon. So radiation for me is just anything that's being emitted by the black hole, whether it be gravitons or observable light for that matter.
Did you have a question? Yeah.
So, at the beginning, you asked us if we knew what string theory was.
Yes.
And then you accepted our answer, and then you have never defined it, didn't need to. We have some, but my view is old, and I thought the string theory had never produced anything, and you've changed my opinion on that.
Mm-hmm.
And so, aside from the fact that strings have frequencies and wavelengths and amplitude, can you give us your brief description? You can take a minute or so to do it.
Sure.
To explain, when you refer to string theory,
Right.
what is it? How would you describe it?
So the question is, and what in its most basic form is, what is string theory? Along with a comment at the beginning that I didn't actually define. I gave a bad talk. In the sense that, in the very defensible sense that I'm talking about a subject that I never defined, because I asked you all if you knew what string theory was, and then didn't. I was like, okay, they know what it is, so we'll go from there. What is string theory? Okay, so since you ask. Let me make maybe one sort of broad, okay, I'll answer your question in a moment, but let me say something first. Exactly what string theory is still a subject of ongoing research. No, I mean it very seriously. So so in our field, one of the things that's very nice about it is that, so I mentioned there's not that many of us. There's various centers for theoretical physics throughout the world. There's institutes that like to host long-term scientific programs where scientists will go and they'll be together for weeks or sometimes months at a time to really try to make progress on some vexing questions to the field, map out directions for research and so on. One of them is at the campus of the University of California at Santa Barbara. It's called the Kavli Institute for Theoretical Physics. And they just had a long-term program, a 3-month program earlier this year whose title was What is String Theory? So I'm not kidding when I say that. It's something that we have a working definition of, lest I give the impression that we're full of it. But exactly what the precise definition is still a matter of ongoing investigation because, in some sense, because our standards are very high. So if you were to take a course in string theory, which unfortunately we haven't been able to offer sometime at UVic, you're not the right person to bug about that. But the way that you start is you take there's a way in which you can take a so-called classical system, like billiard balls, or in this case, just a string, and quote-unquote quantize it to generate, given that theory of things that you can measure and imagine taking a string and exciting it, plucking it, and so on, taking that and out of it getting a quantum mechanical description of that same building block. And that is the starting point for string theory. And what you find when you start doing that is that, you have a string that's moving in some higher dimensional space. That thing as a quantum mechanical theory, we're talking purely Gedanken, et cetera, all the qualifiers from earlier, it forces upon you many consistency conditions, many things that have to be satisfied. Many things in physics, it's kind of up to you to be smart, to come up with what are the right forces or what are the right building blocks and then match that to data and so on. Here, it really hems you in from all sides. For instance, you learn this thing that, the string can't just propagate in any space-time. It has to be propagating in one that obeys, whose shape is governed by a version of Einstein's theory of general relativity. That comes to you. So the gravity, it can't just move in any space whatsoever. It has to move in one that's obeying the laws of general relativity. And furthermore, there's this constraint on the dimension of the space-time, this thorny 10 or 11 that was mentioned earlier, really 10 in that setting. But then that's just the starting point for, sorry, this is the long answer. That's the starting point for the definition, and then you keep going and you learn that there's much more there in this model than what you, the aspiring physicist, who originally wanted to describe, in that case, string-like excitations in QCD, the theory of the strong interaction. There's all sorts of extra ingredients there that you did not put in but are there anyway, including black holes.
So mathematics that you use,
Yeah.
your tools,
Yes.
must incorporate the characteristics, using just as an example, wavelength, amplitude.
Yeah.
And frequency.
The mathematics,
That must be incorporated into the mathematics.
the working mathematics is really, maybe that this helps to hear it. Most of it is an enormous amount of applied calculus. But what are the ingredients that go into it? You need to characterize even just an ordinary string that you could almost hold in your hand first, where all the things that you were saying, amplitude, frequency, etc., those are the possible motions of the string. That is some ingredient that comes along the way. Yeah.
Okay, I think our speaker will be around, and I think we need to draw to a close in the formal Q&A, but I'm sure he will be happy to answer any questions one-on-one after. Thank you very much To the speaker, thank you very much. And thank you very much for being here and participating in Café Scientifique.
How long ago did that? I think a lot of people